Hello, I'm Maurice Dupre, and in this section we're going to discuss one-sided limits and limits at infinity. Let's begin by looking at one-sided limits. First, we have to deal with the notation. The notation for one-sided limits is very similar to the notation for two-sided limits, so you have to look carefully. When we see f of x has a right-hand limit, capital L, at x naught, the notation will be limit underneath x arrow x sub naught with a superscript plus sign, plus indicating to the right. So limit x arrow x sub naught plus f of x equals L is the notation for the right-hand limit. So when you look at a limit symbol, look carefully to see whether or not there is a superscript plus. Likewise, f of x has left-hand limit L at x naught. Similar notation, except for the left-hand limit, we have a little superscript negative sign there, a minus sign. And so you have to look closely for those because they're typically going to be very tiny. Now, let's look at a picture that shows what we mean by this. Here I've got the graphs of two functions. Here's f and another piece of f down here. So in this picture, the limit as x approaches x naught from the right, see the superscript plus there, is the value you get as you come in from the right. Notice if I follow this curve in from the right, it's leading me to this value right here, and that I've denoted capital L with a subscript capital R for the right-hand limit, is the value of the right-hand limit. On the other hand, if we follow the graph in from the left side, you see it's leading us to a different value, what I call capital L with a subscript L for left-hand limit. So in this picture, both those limits exist, both one-sided limits exist, but of course in general you see even if the one-sided limits exist, they can be quite different. Let's look at this picture of the function g. Notice if I try this same procedure coming in from the right, it's telling me the value L, that is the right-hand limit of g would be capital L. If I come in from the left, it's leading me to the same value. So g has both one-sided limits as x approaches x naught, and they both have the same value L. Now look at this picture. Doesn't that look like the picture of a function with a two-sided limit at x naught? In fact, you can see that the function has a two-sided limit exactly when both one-sided limits exist and are equal. So to state this formally, a function f of x has a limit as x approaches c if and only if it has left-hand and right-hand limits there, and these one-sided limits are equal. So in symbols, the limit as x approaches c of f of x equals L, if and only if the limit as x approaches c from the left, see the little superscript negative sign there, of f of x equals L, and the limit as x approaches c from the right, see the little superscript plus sign of f of x equals L. So both one-sided limits must exist and both must be equal. If that's the case, then the two-sided limit exists and is that common value. Well, let's look at an example where we use one-sided limits to answer the question of existence of a two-sided limit. Here, I have the function f of x given with two different expressions. First, it's 3 minus x if x is less than 2, or we use x divided by 2 plus 1 if x is greater than 2. Notice by themselves, each of these expressions is the expression for a straight line. So for instance, if f of x had equaled 3 minus x for all x, it would just be a straight line of slope -1 and y-intercept 3, whereas if f had been given by this expression for all x, it would be a straight line of slope 1/2 and y-intercept 1. Well, if we draw these two lines, the graph looks like this. Here, these two open circles over 2 indicate that f is undefined at x equals 2. So the line x over 2 plus 1 is only used to the right of 2. The line 3 minus x, y equal 3 minus x, would be used to the left of 2. So let's consider now the one-sided limits. Where are we going as we come in to 2 from the left? Notice coming down this line, the value we're led to is y equals 1 at x equals 2. If I come down this line from the right, I'm led, when I get to x equal 2, I'm led to the y value of 2. So that would indicate that the left-hand limit as x approaches 2 should be 1, and the right-hand limit as x approaches 2 should exactly be 2. In particular, if that is the case, then our theorem on one-sided limits related to two-sided limits tells us that the two-sided limit here cannot exist because we would have different values for the one-sided limits. Well, let's compute. Now, to compute exactly the left-hand limit of f of x, so we'll write limit as x approaches 2 from the left, indicating that with the little superscript minus sign of f of x. Well, that equals the limit as x approaches 2 from the left of the expression for f of x when x is to the left of 2. So that's simply 3 minus x. Now, of course, by our theorem on one-sided limits, when I look at that expression 3 minus x, I see it is perfectly valid for all real x, and in fact it has a two-sided limit as x approaches 2, and so therefore our theorem tells us that that will have to equal the one-sided limit, in this case the left-hand limit. So the left-hand limit as x approaches 2 of the expression 3 minus x will in fact be the two-sided limit for 3 minus x, and we know how to do that from our limit rules. It's just 3 minus the limit as x approaches 2 of x, which is simply 2. So we get 3 minus 2, which is simply 1. In other words, our left-hand limit as x approaches 2 of f of x, as x approaches 2 from the left of f of x, is simply 1. That was just what our picture told us. Now let's look at the right-hand limit. Limit as x approaches 2 from the right of f of x. In this case, when we're restricted to being on the right of 2, we use the expression which is valid to the right. Look up here, that's x over 2 plus 1. Well, from our limit rules, when we look at that expression, we know that that has a two-sided limit as x approaches 2, and consequently that two-sided limit by our limit theorem has to equal either of the one-sided limits for that expression. In particular, this right-hand limit has to equal the two-sided limit of the expression x over 2 plus 1. So now I can remove the little superscript plus sign, and now I see how to take the limit of that expression easily. It's simply 2 over 2 plus 1. 2 over 2 being 1, we have 1 plus 1, or 2. And so now, just as our picture indicated, we have that the limit as x approaches 2 from the right of f of x equals 2. So there are our one-sided limits. Notice they are not equal. And so consequently, when it comes to the question of the two-sided limit, it cannot exist. In other words, here, the limit as x approaches 2 of f of x does not exist. Again, why? Because the two-sided limits, in fact, do exist, but they are not equal. Let's look at another example where we examine the one-sided limits for a function. Here I have the function f of x equals x cubed if x is not equal to 1, and 0 if x is equal to 1. We want to graph it to begin with. So consequently, what I'll do is make a quick set of axes here. And we recognize this expression x cubed right off as our cubic curve. And in effect, what's happened here is, notice when x equals 1, 1 cubed is 1. So we've removed the point 1 comma 1 from the cubic curve. So I'm going to mark off unit distances on each axis, and I'm going to start by putting a little open circle there for 1 comma 1. And now I'm just going to draw my cubic curve through that point, but I'll be careful to step over it, and then we just keep going. So there's, well, not perfect, but a drawing effectively of y equal x cubed, which is our f of x, which is valid for x not equal to 1. And what about when x equals 1, we get the value 0. So I'm going to make that dot down there on the x-axis at x equal 1, a big round dot to indicate that when x equals 1, this function gives us the value 0. So there's our graph. Now notice what's going to happen graphically if I take the right-hand limit as we come down, it's leading us to the value 1. If I come in from the left, it's leading us to the value 1. So intuitively here, or pictorially, both our one-sided limits are existing, and we should have the limit as x approaches 1 from the left of f of x equals 1, and that should also equal the limit as x approaches 1 from the right of f of x. These one-sided limits, notice I'm indicating with these little superscripts plus and minus. Now, to actually compute this limit rigorously, what we can say is, for instance, for the left-hand limit, the limit as x approaches 1 from the left of f of x is the limit as x approaches 1 from the left of the expression which is valid to the left of 1. Well, notice when we're to the left of 1, if x is to the left of 1, it's certainly not equal to 1, and so the valid expression is x cubed. But now when I look at the expression x cubed, we know that that has a two-sided limit at x equal 1, namely 1. And so consequently, since it has a two-sided limit, its two-sided limit must equal the left-hand limit. So therefore, we have the limit as x approaches 1 of x cubed. Now we know that that is 1. So that's an exact proof, you see, that the left-hand limit of f of x as x approaches 1 from the left is equal to 1. What about from the right? Well, let's change this little superscript minus to a superscript plus. Coming to 1 from the right, the expression valid on the right, well, to the right of 1, x is not equal to 1, so still it's x cubed. And so we have the right-hand limit as x approaches 1 of x cubed, but x cubed again has a two-sided limit at x equal 1, and so consequently that two-sided limit must be the one-sided, in this case the right-hand limit, which is 1. So you see both ways, and just to emphasize this, I'll put plus or minus here, both of these one-sided limits give us 1, and so that means in particular that this function has a two-sided limit, and that two-sided limit is that common value. And so we have demonstrated here using one-sided limits that this function has a two-sided limit at x equals 1, and the limit as x approaches 1 of f of x is in fact equal to 1. Let's look at another example where we examine a one-sided limit. Here I have the limit as x approaches negative 0.5 from the left. Notice that little superscript negative sign up there is telling us we're dealing with a one-sided limit. Now, whenever you're presented with a one-sided limit to calculate, since we know how to calculate two-sided limits so well, you should always ask yourself, does this expression have a two-sided limit? Because if it does, our theorem relating one-sided limits to two-sided limits would tell us that either one-sided limit has to be the same as the two-sided limit. So let's look at this. Here we're examining the behavior at negative 0.5. If I put negative 0.5 in for x, is that denominator 0? No. So that means, in fact, what's inside this square root will have a limit of two-sided limit at x equals negative 0.5. And so consequently, since the square root of that will give us the overall two-sided limit, we're dealing really with a situation where we in fact have a two-sided limit at negative 0.5. Well, that two-sided limit must be the left-hand limit, and so we can simply drop that little superscript negative sign. So really we're dealing with the limit as x approaches negative 0.5 of the square root of x plus 2 over x plus 1. And so now from our limit rules, we know that that will just be the square root of the limit of the numerator divided by the limit of the denominator. So that will be negative 0.5 plus 2 divided by negative 0.5 plus 1, all inside the square root. So we end up with 2 minus a half, that's 1.5, and let's write that as simply 3/2. And 1 minus a half is simply 1/2, all inside the square root. And of course, these twos cancel, and we simply end up with the square root of 3. So the square root of 3 then is the left-hand limit as x approaches negative 0.5 of our expression square root of the quantity x plus 2 over x plus 1. Let's look at an example of one-sided limits where we have to deal with the absolute value function and see what can happen. Here, I want to look at both the right-hand and left-hand limits as x approaches negative 2 of the expression x plus 3 multiplied by the absolute value of the quantity x plus 2 divided by the quantity x plus 2. Well, notice x plus 2 in the denominator is kind of a red flag. We immediately have to ask ourselves what's going to make that 0, and notice if x is negative 2, the denominator is 0. And so that's what's really going on here. We want to look at the limit as x approaches negative 2 from either side of negative 2. Now notice what's going to happen if x is to the left of negative 2. That would mean it's a negative number which in absolute value is bigger than 2. So if I take a number to the left of negative 2 and we add 2, we'll still be negative. So this denominator is negative to the left of 2, whereas because there's absolute value in the numerator, it's always positive to the left of 2. And so positive divided by negative is negative. Other than that, notice the numerator and the denominator have the same absolute value, and so consequently the quotient can only be a plus or minus 1. So when the denominator is negative, we have to be getting negative 1. And so consequently, as x approaches negative 2 from the left, we're dealing with negative 1 times the quantity x plus 3. Let's look what happens to the right of negative 2. If x is bigger than negative 2, then x plus 2 will be positive. That is, if I take a number that's bigger than negative 2 and add 2 to it, I'll get a positive number, and so positive over positive is positive, and so now we're getting plus 1. So what we're having here is the fact that this limit is equal to either the limit as x approaches negative 2 from the left of negative x plus 3, or it's the limit as x approaches negative 2 from the right of positive x plus 3. That is, the left-hand limit is the limit of negative x plus 3, and the right-hand limit at negative 2 is just the limit as x approaches negative 2 from the right of x plus 3. Notice both of these expressions in and of themselves would have perfectly good two-sided limits, and so consequently the limit as x approaches negative 2 from the left or the right of x plus 3 times the quantity absolute value of x plus 2 divided by x plus 2 is going to equal the limit as x approaches negative 2 of negative x plus 3 when we come in from the left. I'll just put from minus. And the limit as x approaches negative 2 of x plus 3 itself when we come in from the right. Of course, coming in to negative 2 here of negative x plus 3, we just replace the x by negative 2, and we get negative 2 plus 3 is 1 inside the parenthesis with a minus sign out front, becomes negative 1, whereas down here, as x approaches negative 2 we're going to get negative 2 plus 3 is plus 1. And so we can summarize this by saying the limit as x approaches negative 2 from the right or left of the quantity x plus 3 times absolute value of x plus 2 divided by x plus 2 is plus or minus 1, with plus going with plus here and minus going with minus. Now let's discuss infinite limits, that is, limits at infinity which are finite in value. Our notation for a finite limit at plus or minus infinity is that f of x has limit capital L as x approaches infinity is denoted limit underneath x arrow infinity of f of x equals L. So when you see the x arrow, this 8 on its side, that's indicating the limit as x approaches infinity of f of x. Likewise, f of x has limit L as x approaches negative infinity is simply denoted x arrow negative infinity underneath the limit symbol. Okay, so now the next question would be, how can x approach infinity? Well, to get to this concept, let's begin by thinking of big numbers as close to infinity. Somehow we have to get at a concept of closest to infinity. And then next, of two big numbers, realize that the largest is closest to infinity. If you have any finite set of big numbers, then the biggest one, the largest of them all, is the one that's closest to infinity among all those numbers. So finally, third, if m is a big number, then when you see x greater than m, that means x is closer to infinity than m. And so now, thinking in terms of limits as being like as x gets close to something, f of x gets close to something, then we can make this into a nice definition. We say that f of x has the limit capital L as x approaches infinity, and write limit x approach infinity f of x equal L if for every number epsilon greater than 0 there exists a corresponding number m such that for all x greater than m implies absolute value of f of x minus capital L less than epsilon. So let's look and see what this means in terms of closeness. What we're saying here is no matter how close you specify that f of x has to be to L, there is some level of closeness to infinity that would be specified by some big number capital M, such that whenever x is closer to infinity than m, the f of x minus L, an absolute value is less than epsilon. That is, the f of x is close enough to L. Now, the same thing applies to negative infinity. That is, we just reverse the order. Close to negative infinity means less than some very, very negative number. We say that f of x has the limit L as x approaches minus infinity, and write limit as x approaches negative infinity f of x equal L if for every number epsilon greater than 0 there exists a corresponding number n such that for all x less than n implies absolute value of f of x minus L less than epsilon. So what we're saying here is, here this epsilon is a specification of how close we want to be to L with the values f of x. And so what we're saying is no matter how close you're required to be, the f of x will be that close provided the x is close enough to negative infinity. That close enough being simply specified by a number n, which is very negative. Now finally, the way we apply these is in the case of a horizontal asymptote. A line y equal b is a horizontal asymptote of the graph of a function y equal f of x if either the limit as x approaches infinity of f of x equal b or the limit as x approaches negative infinity of f of x equal b. So consequently, if I want to draw a picture of this, here's what we can think of. Imagine here's my axes, and let's draw a dashed line, for instance, right here to be the line y equals b. And so, for instance, if the function has the limit as x approaches positive infinity equal b, as we go out to infinity, it gets ever closer to that horizontal line y equals b. Whereas if y equals b satisfies the limit as x approaches negative infinity of f of x equal b, it's still a horizontal asymptote. In this case, the picture would look like this. In other words, as we go towards negative infinity, the graph of the function gets ever closer and closer to y equals b. Let's look at an example where we compute limits at plus and minus infinity for a function. Here, I want to compute the limits at plus and minus infinity of g of x, where g of x equals 10x to the 5th plus x to the 4th plus 31, all divided by x to the 6th. So to do this, I will put the expression in for g of x. And now, typically, when we're looking at limits at plus and minus infinity, one limit that we easily know is the limit of 1 over x as x approaches infinity. That's 0. The limit as x approaches plus or minus infinity of 1 over x equals 0. That's a kind of a basic fact that you should keep in mind. So that would mean that any positive power of 1 over x will also go to 0 as x goes to plus and minus infinity. And so consequently, the technique when we're faced with these quotients of polynomials is to look at the biggest power of x you see and divide every term by that x raised to that power. So for instance, looking at all the terms, I see x to the 6th power is the highest power of x, and so I'm going to take each term and divide by x to the 6th. So I'll have the limit as x approaches plus and minus infinity of 10 times x to the 5th divided by x to the 6th is simply 1 over x, plus x to the 4th divided by x to the 6th is 1 over x squared, which is 1 over x quantity squared, and then plus 31 over x to the 6th. Well, I can write that as 31 times 1 over x raised to the 6th power. And so now here is our limit, and notice each term has a factor of 1 over x to some power, and so that means as x goes to either plus infinity or negative infinity, that 1 over x goes to 0. So we get 10 times 0 plus 0 squared plus 31 times 0 to the 6th. All that is simply 0. Let's look at another example of limits at infinity. Here I have the function 2 square root of x plus x to the negative 1, all divided by the quantity 3x minus 7, and I want to compute the limit as x approaches infinity. Of course, I cannot go to negative infinity here because square root of x is not even defined for negative x. So consequently, remember our technique, and it'll still work here as long as every term is simply a power of x, even if those powers aren't integers. We can use the same technique. Look for the highest power of x. In this case, I have, for this term, x to the 1/2 power, x to the negative 1 power, x to the 1, and in effect, x to the 0. And so of all those, the first power here is the highest. So divide each term by x. And so we have the limit as x approaches infinity of 2 times square root of x over x is 1 over square root x, plus x to the negative 1 divided by x, we could say that's 1 over x squared. And 3x divided by x is simply 3 minus 7 divided by x. And so now what's going to happen to each term as x goes to infinity? Well, the limit of 1 over square root of x will be the square root of the limit of 1 over x as x approaches infinity. So that's the square root 0, which is 0. So we get 2 times the square root of 0 plus, here we'll have 0 squared divided by 3 minus 7 times 0. And so notice 0, 0, the numerator is 0, the denominator is 3, and we get 0. If this had been upside down, notice the highest power would have then been in the numerator, and we'd end up with a situation of 3 over 0 here, and our limit rule would break down, remember, because we can't use the quotient rule when the denominator is 0. But in that case, the limit as so far doesn't exist, or we have to deal with infinite limits. Well, we've discussed one-sided limits, and we've discussed limits at plus and minus infinity. Now that you've seen some of these problems work, you should try some on your own.